I'm working with a dataset containing 100 samples. These samples are categorized into 3 classes, A, B, and C. Think of it like sorting 100 objects into 3 different boxes. I've set the number of folds for each repetition of the cross-validation to 5. In simpler terms, I'm dividing my data into 5 groups for each round of testing. I'm repeating my 5-fold cross-validation process 3 times to get more reliable results. Think of this like repeating the 5-group division and testing process 3 separate times. The distribution of the samples is not equal across all 3 classes. Class A and B have 30 samples each, while Class C has 40 samples. This is a technique I'm using to split my data. It ensures each group has a similar class distribution to the entire dataset, even when classes have unequal numbers. Since I'm repeating the 5-fold process 3 times, 5 folds * 3 repeats, I end up with a total of 15 different folds or groups of data for testing. I'm asking you to determine which statements about the properties of this method are correct. This is the method I'm employing to validate my model. It's a type of cross-validation that uses stratification to maintain class distribution across each split. Think of it as a special kind of testing that keeps the groups balanced. I'm using RepeatedStratifiedKFold, which is a cross-validation technique from Sklearn. It's designed to create folds that maintain the proportion of different classes in the dataset. It's like making sure each group is fairly represented in every round. We have 100 data points, categorized into 3 classes, A, B, and C. Class A has 30 samples, B has 30, and C has 40. Notice the imbalance. C is slightly overrepresented. I've set the number of folds per repetition to 5. This means each repetition will divide the dataset into 5 separate groups for training and testing. The entire process will repeat 3 times. Each time will have new folds, helping to reduce bias and get more reliable results. I will have a total of 15 folds, 5 folds, repetition * 3 repetitions. Because of the stratification, the proportion of A, B, and C is maintained in every one of these 15 folds, as much as possible. Each fold will have a similar class distribution as the whole dataset. Since we repeat the process 3 times, each data point will appear in exactly 3 folds. This gives the model more opportunities to see and learn from each data point. I'm working with a dataset containing 100 samples that are categorized into 3 classes, A, B, and C. These are the settings I'm using for my analysis. I've set the number of folds to 5. That means I will divide my dataset into 5 separate groups for cross-validation. I'm repeating the 5-fold cross-validation process 3 times. This helps me get a more reliable assessment of the model's performance. Because I'm using 5 folds and repeating the process 3 times, I will end up with a total of 15 folds. 5 folds * 3 repeats equals 15 folds. Each sample will appear in exactly 3 folds because the entire process of creating 5 folds is repeated 3 times. I'm using a method that ensures each fold contains roughly the same proportions of classes A, B, and C as the original dataset. This helps to avoid biased results. I'm using RepeatedStratifiedKFold, a technique in Sklearn that does stratified K-fold cross-validation repeatedly. It's like doing regular stratified K-fold cross-validation several times to get a more reliable picture of your model's performance. This means I divide my data into 5 folds each time I do the cross-validation. Think of it like cutting a cake into 5 slices. I repeat the 5-fold splitting process 3 times. So, that's like baking 3 cakes and slicing each into 5 pieces. That gives me a total of 15 folds, 5 folds. Cake * 3 cakes equals 15 folds. I now have 15 different ways to train and test my model, which gives me a more robust evaluation. Because I repeat the whole process 3 times, each data point shows up in exactly 3 of those 15 folds. Each time I repeat, I get a different set of folds, not the same folds over again. That's the key to get a more reliable model evaluation. I'm looking at a dataset with 100 samples. These samples are categorized into 3 classes, A, B, and C. The approximate distribution is 30 samples in Class A, 30 in Class B, and 40 in Class C. This is important because we'll use this information to understand how the cross-validation technique distributes samples. Here, I'm defining the number of folds for each repetition of the cross-validation process. 5 folds mean that the data will be split into 5 groups: a training set and a testing set. I'll use each of the groups as the testing set once while the rest of the groups become my training set. This helps to create different training and testing splits for evaluating a model. I'm setting the number of times I want to repeat the entire 5-fold process. Repeating helps to get a better, more stable estimate of the model's performance. I will run this 5-fold cross-validation 3 times, each time creating a new set of folds. Each sample appears once in one fold in each of the 3 repeats. This is the specific type of cross-validation I'm using. RepeatedStratifiedKFold combines 2 important techniques: stratified sampling and repeated cross-validation. Stratified sampling makes sure that the class proportions, A, B, and C, remain consistent in every fold. That is, the training set and testing set for each fold retains the class proportions consistent with the whole dataset. Repeating the cross-validation process creates multiple different sets of folds, making the model evaluation more robust. Because I have 5 splits per repeat and I'm repeating the process 3 times, I will get a total of 15 folds. 5 splits * 3 repeats equals 15 folds. This means that each sample will appear in the testing set for 3 of the 15 folds. I'm using RepeatedStratifiedKFold, a technique in machine learning that helps us evaluate the performance of a model. It's like repeatedly testing your model with slightly different data splits to get a more reliable idea of how well it will generalize. The repeated part means we do this multiple times, and stratified ensures that each data split maintains a similar class distribution, which is crucial for fair evaluation. K-fold refers to the number of splits made in each repetition. We're working with a dataset containing 100 samples split into 3 categories or classes: A, B, and C. Each category has approximately 30, 30, and 40 samples. I'll use RepeatedStratifiedKFold to divide this data for cross-validation. I will use 5 splits in each repetition with 3 repetitions in total. The quiz tests my understanding of how this method divides the data. This describes the dataset. It's like having 100 different items, 30 each of type A and type B, and 40 of type C. I will use this distribution to answer multiple choice questions on how RepeatedStratifiedKFold works with this data. These are settings for my RepeatedStratifiedKFold. (n_splits equals 5 means I'll split the data into 5 folds in each repetition. (n_repeats equals 3 means I'll repeat this splitting process 3 times, creating different sets of folds each time. This introduces the multiple choice questions I need to answer based on my understanding of how RepeatedStratifiedKFold would divide the given data. This statement is about whether each fold will have a similar proportion of classes A, B, and C as the whole dataset. This question checks if I understand the total number of folds created by the process. This statement explores how many times each data sample will be used in the different folds. This statement asks about whether the folds created during the repetitions are similar or different. A visual representation of the RepeatedStratifiedKFold process that is not needed to answer the given question. A visual representation of the dataset that is not needed to answer the given question. A visual representation of one repetition of splitting into 5 folds that is not needed to answer the given question. A visual representation of repeating the process 3 times that is not needed to answer the given question. A visual representation of the total number of folds that is not needed to answer the given question. I'm using RepeatedStratifiedKFold, a technique for splitting data into multiple folds for cross-validation. It's a powerful method to evaluate the performance of a machine learning model reliably. This means I'm splitting the data into 5 different folds in each repetition of the cross-validation process. Think of it like dividing a deck of cards into 5 piles. I will repeat the whole process of creating the 5 folds 3 times. Each repetition generates a different set of folds. It's like shuffling the deck of cards and dividing it into 5 piles 3 separate times. The algorithm ensures that the class distribution, the proportions of different categories, in each of the 5 folds remains similar to the overall distribution. It keeps the balance across the folds. 5 folds per repetition, multiplied by 3 repetitions equals 15 folds in total. It's a simple multiplication. 5 folds, repetition * 3 repetitions equals 15 folds. In each of the 15 folds, I will see a roughly equal proportion of the 3 classes, A, B, and C, mimicking the original data's class distribution. Because I repeat the process 3 times, each data point shows up in 3 different folds. It's like each card appearing in 3 different 5-card hands. The key feature is that each repetition produces a completely new set of folds. The different shuffles result in different hands. That's what this is, a multiple-choice quiz. It's time to determine which of the given statements correctly describe repeated stratified-KFold's behavior. This statement highlights the stratified aspect. Do you think each fold will roughly maintain the original class balance? Let's verify. Does the calculation in the description match your understanding? Does this align with the way repetitions work? This assesses your understanding of the key difference between repeated KFold and standard KFold. Think about how the algorithm creates the folds in each repetition.